This sixth lecture on Schrodinger equation in 1D. Today we shall discuss rectangular potential barrier of height v0. The situation is this: this is x-axis, this is 0, minus a, plus a, then this is the potential axis v of x. This is v is equal to 0, v is equal to 0, and here v is equal to v0. This is a potential barrier. So the particle is more experiencing a sudden rise in potential, and that persists for certain width. Here it is the 2a is the width of the barrier, and then again potential becomes the same as the left. So we define the potential as v of x is equal to v0 for mod x less than a and is 0 for mod x greater than a, and there is a discontinuity, finite discontinuity at x is equal to plus minus a. As usual, we denote the three regions as 1, 2, 3. So the region 1 is to the left of minus a, region 3 is to the right of a, and region 2 is in between plus minus a. The initialization of the problem is that a free particle of mass m and energy E moving in region 1 from left to right encounters the barrier. So this is the initialization of the problem. This is a free particle coming, and this is incident wave. If we write the Schrodinger equation in region 1, then the Schrodinger equation in region 1 is phi 1 double prime plus k1 square. Phi 1 is equal to 0, where k1 square is equal to twice m e upon h line square, and the solution is a e to the power plus I k1x plus b e to the power minus I k1s. This is the incident wave phi I, and this is the reflected wave phi r. So for region 1, this is in region 2, the solution, similarly the solution in region 3 is f. We preserve constant c and d for region 2. Since there is no more discontinuity towards the right of x is equal to a, that is in region 3, so there is no provision of getting reflected wave. So this is the final transmitted wave. Now the solution in region 2 depends on the relative magnitude of E and V0. We consider the case 1 with E greater than V0, the scattering case, the so-called scattering case. Here we call k1 square, k1 square is equal to twice m e upon h line square. Here the wave function is phi 2 double prime plus k2 square phi 2 is equal to 0, So where k2 square is equal to twice me minus v0 by h line square, since e is greater than v0 and this is greater than, and phi 2 is equal to c e to the power I k2x plus d e to the power minus I k2x. Now what happens? This incident wave falls on the left side, left wall of the barrier, and a part is reflected back. This is given by phi r, and some wave amplitude enters in the region 2 and moves towards the right. This is represented by this part, and again there is a reflection part in region 2. This is represented by this, and finally some wave escapes into region 3, which is given by this. People generally ask for the transmittance, that is, what is the probability that the particle will be received in region 3. So we need to for that we need to calculate T transmittance is equal to JT by JI, and this is equal to simply f by a modulus square. We have performed similar calculations earlier, so I am not going into the detail of JT and JI. This gives you JI, this gives you JT. Now how to relate F and A? If we apply the boundary condition is that phi 1 at minus A is equal to phi 2 at minus A, and phi 1 prime at minus A is equal to phi 2 prime at minus A. This gives us two relations involving A, B, C, D, and K1, K2. And if we apply the boundary condition at the right wall, we will have phi 2 at A is equal to phi 3 at A, and phi 2 prime at A is equal to phi 3 prime at A. Exactly similar thing we have done in the case of scattering case with potential well. So ultimately we can solve this equation and we get this as in terms of energy. This relation becomes and we know that the transmittance is 1 when sine 2k is 1. For t to be 1, we must have sine 2k to a is equal to 0 is equal to sine of n pi, and which gives us to the fact that 2a is such that 2a, the width of the well is such that it accommodates n times lambda 2 by 2, that is an integral number of half de Broglie wavelength in region 2. So if this condition be satisfied, this transmittance is 1, and this effect is also sometimes called the Ramsauer effect. Now we come to the second case, that is the bound state aspect. In this case, a particle of energy E less than V0 impinges on the left wall of the well, that is a free particle moving from left to right in region 1 encounters a barrier at x is equal to minus a, or so to strictly speaking the left end of the barrier at x is equal to minus a. Here in this case the wave function in region 2 will be where ρ2 square is equal to and the solution is ρ2x. We cannot eliminate either of the parts because this solution is applicable only in between these two when both the parts remains finite. So this is the solution. Again we apply the same set of 4 boundary conditions, and if we compare the other the scattering case, the wave function was this. So from scattering case we can get back the result of bound state case by replacing K2 by I ρ2. This is the replacement. So the first thing is that we have sin x, sin square x. Sin x can be written as e to the power ix minus e to the power minus ix by 2I. If we replace x by iy, then what we will have, sin of iy will be e to the power minus y minus e to the power plus y by 2I. This is equal to, if we take this is I times sine hyperbolic y, so that the factor that we encountered in sine 2k2a is replaced by I sine hyperbolic twice ρ2a. This is the transformation. So we come to the expression for transmission coefficient. To come to the transmission coefficient, the original we have transmission coefficient was like this: 4k1 square, recall, and k2 square is minus ρ2 square. Then we will have again 4k1 square minus k2 square is this should be then we had a term k1 square minus k2 square, so this is rho 2 square, and then we had sine hyperbolic sine hyperbolic 2 rho 2a whole square. So we see that this is the minus sign, this is the minus sign, and all, if we adjust all these things, we will have the expression 4k1 square rho 2 square plus k1 rho plus rho 2 whole square sine hyperbolic square this is the expression for the transformation coefficient. In terms of energy, this expression becomes this is the expression. In coming from here to there, we have used the definition of k1 square and k2 square, rho 2 square. These two definition has been used. Now let me consider x to be, consider this, for x to be much greater than 1, sine hyperbolic square of x is equal to 1/4 e to the power x minus e to the power minus x whole square. So this is 1/4 e to when x is very high, we can neglect this term because it goes to 0, and 4 is insignificant in comparison of e to the power x, so it is 1/4 e to the power 2x. So if we apply this approximation here, for 2 rho 2a is much greater than 1, we have t is approximately 1, and this term is very high, so we can neglect this one. So this is phi 0 square upon 4e v0 minus e, and for sine hyperbolic square we write 1/4 e to the power what, this is 4, already it was 2, so 2 times 2, 4 rho 2a, which is equal to, this 4 makes it 16 in the numerator, 16 e minus v0 by e, and in the denominator we have v0 and e to the power 4 rho 2a. This is the famous Gamow formula for alpha decay. Gamow formula for alpha decay. My intention for studying this complicated calculation is to get the Gamow formula. So what we have, this this statement allows to explain the decay of alpha particle from radioactive nuclei. By this we end our discussion on rectangular potential barrier. In this calculation we have escaped the lengthy calculation part by using boundary conditions and other things, but with our experience on the similar studies from potential well, we have arrived at the physically interesting result, that is the expression for the transmittance, and made the subsequent discussion on it. In the next class we shall consider another important potential, that is the delta potential, and we shall see that when the potential has an infinite discontinuity, the momentum of the that is the first derivative of the wave function is no more continuous, and we shall study the bound and scattering aspect of a particle subjected to one-dimensional delta potential.